Hello, psychology students. This is Mrs. Politsky, and I have notes from Module 8, Sensation, and now we're going to talk about the other senses. So let's talk about taste. Taste is a chemical sense. You have taste receptors that are located on the surface of your tongue, and these receptor cells, for the most part, detect roughly 5 different tastes. It used to be years ago 4. So salty, sweet, sour, and bitter. And the new one is called umami. And umami is kind of a weird thing. It's kind of that savory, meaty taste that you might find in like Oriental foods. But for years, we used to focus primarily on the salty, the sweet, the sour, and the bitter. And for the most part, as humans, we have a tendency to be attracted to some taste over others. And particularly when we talk about salty and sweet, for some reason, that's hardwired in our brains to kind of like those things. And even as infants, we have a predisposition to seek out things that are salty and sweet, particularly when we talk about infants who are nursing. Taste receptor cells can also be damaged. If you've ever burnt your tongue, so like heat, or not necessarily spicy heat necessarily, but if you've drank like maybe hot coffee or hot chocolate, or ate a slice of pizza that had really hot cheese, those kind of things can damage the receptors, those taste buds. And for a time there, you may not be able to detect in those areas where there is damage. Over a long period of time, you could damage those taste receptors indefinitely. Other things that might damage it are things like tobacco smoke. Individuals who are lifelong smokers have a tendency not to be able to taste foods the same way as people who are non smokers. About of the quarter of our population are dubbed what we call super tasters. And this is something that was dubbed by a researcher named Linda Bartoshuk and her colleagues. They have super tasters, that is, they have an abundance of taste receptors, particularly ones that are more sensitive to things like salty, sweet, and sour, opposed to the bitter. Even today, super tasters, with their enhanced sensitivity, have certain sensitivities to like alcohol's bitter taste. Most super tasters don't like bitter food. So, for example, things like broccoli, which is kind of a bitter food unless you're dousing it with things like cheese and such. Um, if you're a super taster, you're going to be turned off by that. You're probably not going to like to drink coffee. You're probably, again, going to stay away from alcohol, opposed to individuals who, um, have a higher tolerance for bitterness. And what this research has kind of proven is that super tasters, for the most part, are probably less likely to become alcoholics because of the fact that they don't like the bitter taste of the beverage. Anyway, another quarter of the population are what we call non-tasters, meaning that they really don't taste um, food maybe with the same intensity as the rest of us. And sometimes that happens with age or because of certain accidents. So, needless to say, you're either going to love the taste or you're not going to really taste much. And for that, that might make a person, maybe lose some of their appetite. So, looking at the diagrams here, we're going to talk a little bit about our taste receptors and such, and really kind of looking at our receptor cells or the taste buds themselves. But to kind of focus in here before we kind of go into all this, speaking of like the sweetness and the bitterness, people who have kind of done research here and tried to track where the sensitivity zones are, bitterness, a lot of what we taste that is bitter usually happens towards the back of our tongue. If you've ever had like an experience with like medication, uh, medication has a tendency to be bitter, and that maybe is a good thing because of the fact that if it has that bitterness, we're probably less prone to abuse it, just like what we mentioned with alcohol. Sour is kind of on the side. So if you've ever had like a sour candy and your tongue kind of like curls in on itself, that's part of the reason why. Salty and sweet, kind of towards the front of our tongue. So if you enjoy things like candies or certain treats that you have to lick, that's usually hitting that first part of the tongue. Or if you're a person who likes your salty popcorn or chips, again, that's kind of where that's hitting the tongue itself. So anyway, uh, the tongue itself contains sense receptors for taste, but the sense of or smell helps us distinguish many of the different tastes. So, in a way, smell and taste really do walk hand in hand. The taste receptors on the tongue are called papilla, and each papilla has as many as roughly 200 taste buds. And so, what you see here in the diagram, kind of in the circle, kind of up into the left hand corner here of our diagram, is an example of that. Okay. This in turn, which in turn contains a number of receptor cells. These receptor cells are called the microvilli. And if you take a look at the microvilli, they are kind of like hair-like projections. So if you're looking at the diagram near the top, there kind of looks like there's little white, hairs, if you want to call it that. There were projections. These are the things that, help us figure out what we're tasting. Saliva, for the most part, will coat our tongue and it will kind of work with helping to send those chemical messages um, or stimulate the receptor cells, which and then will transduce this chemical energy into some type of neural signal to be transmitted back to the brain. Smell, on the other hand, is also a chemical sense, just like taste is. But molecules are given off by any substance that circulates in the air, good, bad, or indifferent. And when these molecules reach the upper nasal passages, olfactory cells that project from the brain can help us produce these smells. We usually talk about it in the terms of this odorant binding protein, and sometimes it's referred to OBP. Uh, our sense of smell is activated by this protein. And as we breathe, there's a fine mist of that OBP. So if you would take your hand up to your nose and you would exhale, you might feel a certain amount of moisture there. That's what we're talking about. But this OBP is sprayed through the duct in the tip of the nose, and the protein binds with airborne molecules, and that activates the receptors for the sense. And these receptors are located high in each nasal cavity and a patch of tissue known as the olfactory epithelium, about half the size of a postage stamp. So it's a pretty small little patch of tissue there. And it's packed with millions of these receptor cells. These cells will die and be replaced roughly every few weeks. So it's possible that over time certain smells might not necessarily be as annoying to us as humans as they once were. So again, looking at the diagram here, you can see the olfactory epithelium kind of in this vicinity, and there's a small patch there that has those cells, and that's what's going to happen. What's interesting is this is located really close to the frontal lobe of the brain, and a lot of people say that it does not require, at least for the sense of smell, processing to go to a separate part of the brain for interpretation. So, like when we talk about like the visual sense and the auditory sense, they go to like an auditory or a visual cortex located in special lobes of the brain. But in the case of smell, it's like right there. So there really isn't a locality that we talk about, but for the most part, the frontal lobe is kind of that processing place. Anyway, unlike taste cells, the olfactory cells do not regenerate when they're damaged. And their number, for the most part, will decrease as we get older. So many elderly individuals have noticeably decreased senses of smell. That can be kind of dangerous. But anyway, smells are processed by the olfactory bulb not necessarily within the brain itself, but the olfactory bulb is located just right next to the frontal lobe of the brain. So, yeah. Anyway, the taste and smell can interact to produce flavors. Odors that normally travel up the nasal passages from the back of our throat are blocked when you have a head cold. Um, you are left with just taste alone, and sometimes that doesn't necessarily make taste as intense as it used to be, and things may not taste so well. Hence, you might not eat as much when you've got a cold. Only a few molecules of the substance are needed to trigger our sense of smell. Decaying cabbage or lemons or rotten eggs, all those kind of things. Doesn't take much for us to identify. Anyway, according to one estimate, the sense of smell is about 10,000 times as sensitive as or sense of taste. Our noses contain at least 1,000 different types of smell receptors, each of which specializes in identifying one specific type of smell. And we can distinguish between different smells throughout. Um, Percentage wise, about 90% of all people can identify the smell. Oh, there we go. The smell of coffee, 80% the smell of leather, 70% the smell of bubble gum, 60% the smell of bologna, and about half can identify things like turpentine, which is like paint remover, vinegar, honey, or even vanilla. Women are better at distinguishing the sense of smell than men. The sharpest time period is basically when a woman is between her 20th and 40th birthday. Women can identify their child or their infants by a sense of smell just hours after giving birth, and vice versa. The babies can do that as well. It's really amazing. uh, Individuals who have lost their sense of smell, there's a term for that. That's anosmia, and that could happen if there is damage to um, the olfactory epithelium or the olfactory bulb. Our sense of touch. This is one of the basics when we talk about senses of pain, temperature, and pressure. Pressure, for the most part, people react to pain and pressure a little differently. When we talk about temperature, people are a little more, um, will react differently to maybe warmth. And then pain, and I think maybe pain and pressure here need to be flip-flopped, but this comes from the force that's caused by displacement of the skin. Anyway, sensory adaptation occurs quickly. Some parts of our body are more sensitive. Our, for the most part, face and fingers are probably the most sensitive to touch. The least sensitive is our back and our legs. An itch results from a general stimulation of pain receptors. So if the pain receptors for some reason are, being triggered, we might feel like we need to itch or scratch someplace. Ronald Milzak and Patrick Wall, for the most part, proposed a theory called the gate control theory of pain. And this gate control theory, for the most part, is dealing with pain signaling systems that consist of a pattern of neural or nerve impulses transmitted to the brain through the neurological gate in our spine. Intense emotion can block the pain stimuli. So if you're really hyped up or really angry, it might have that tendency to block pain. Fear, perhaps. Pain messages from the body travel on one set of nerve fibers in the spinal cord. Other kinds of sensory information travel on another set of nerves. And some of these are a little slower and faster. It's kind of like, the diagram below, if you've ever held onto the pipes for hot and cold water, the cold water pipe is typically obviously cold. Hot water could be very, very warm, but when you put them together, um, cold and hot, it might change that sensation into that of very, very hot. So anyway, some conditions of the non-pain fibers can actually close the pain gate. And this is why other touch sensations can partially block the sensation of pain. Our skin uses no specialized receptor cells other than just neurons. And these neurons do have specialized dendrite endings, however, which modify the manner in which uh, they transduce physical energy into a neural firing or an action potential. Humans, on average, if you're a 6 foot human, not all of us are that tall, but 6 foot human has roughly about 21 square feet of skin. And this provides a lot of things: protection from our environment, it holds in our fluids and regulates the internal temperature, provides a place for our nerve receptor cells as well. Other bodily senses. There is a sense called the kinesthetic sense. This is kind of sensing our position and movement of our body parts. This relies on receptor cells located in our muscles and our joints. A more common disruption of our kinesthetic sense happens when your leg falls asleep. And this occurs when you've held your leg in the same position for so long that the nerves temporarily stop transmitting kinesthetic information. And hence, when you stand up, it just, yeah, it feels all weird and wacky. The other is the vestibular sense, and this is a sense of body orientation and balance that relies on the semicircular canals within our inner ears. It relies on the fluid-filled semicircular canals perched on top of the cochlea. And the best way to kind of mess with this is to spin in circles until you become dizzy. Sometimes, if you've had like a head cold or sinus infection, or if you have an ear infection, this sense, vestibular sense, can get all out of whack, and a person can feel incredibly dizzy as a result of that. All right. Thank you very much.